Let's consider different kinds of discontinuities seen in rational functions. Now, let me take an example first. Okay, let me write a very simple rational function, a reciprocal of a quadratic function in factored form. Let's say f of x is equal to 1 over x plus 1 times x minus 3. Now here, if you notice, in the denominator we have two factors, right? Either one of them could be 0. If you divide by 0, then you get an infinite number. Or we say that division by 0 is not possible, and that leads to a discontinuity. This kind of a discontinuity is called a vertical asymptote, correct? So if I sketch a graph of this, what should I expect? So here, at x equals to minus 1, my function will be 0, 1 over 0. And so, that is not allowed in the domain of the function. It will make the function discontinuous at x equals to minus 1. So, let's say this is our minus 1. So here, we will see a vertical asymptote at x equals to minus 1. Similarly, for x equals to plus 3, we get a 0 in the denominator, which is not allowed since 1 over 0 is not permitted. So the function is again discontinuous at x equals to 3. Let's say this is our x equals to 3. Now at these 2 points, we have discontinuity in our function, and these kinds of discontinuities are called the vertical asymptotes. So, without getting into details of how to sketch it for the moment, if we try to sketch this graph, we will get a graph which is kind of like this. Where the local maximum will be right in the center of minus 1 and 3, which is minus 1 plus 3 equals to 4 divided by 2 is 2, right? So this point is minus 1 plus 3 is 2, and 2 divided by 1 is 1. So this point will be 1, the x value. And the y value you can get by plugging in 1 here, and you get 1 plus 1, 2. So 2 times 1 minus 3 is also minus 2. So 2 times minus 2 is minus 1 over 4. So this coordinate here will give us local maximum, which is 1 minus 1 over 4. Correct? And this side behaves like a reciprocal of a linear function. If you draw a parabola, your parabola will be kind of like this. This is your parabola. We'll call g of x equals to x plus 1 times x minus 3, right? And the reciprocal of parabola I've drawn in red, right? But anyway, here we are concentrating more on discontinuities, and the type of discontinuity which we see in this function is vertical asymptotes. So we have two vertical asymptotes here, and their equations are x equals to 3 and x equals to minus 1. Now, normally you will see vertical asymptotes as the discontinuities. Now let's consider another function, and this time let me say h of x is equals to x over 2x minus x squared. In that case, what happens? What we see from here is we can factor the denominator, and if we do so, we get x over, we can take x common, and we get 2 minus x. Now, here we have x as a common factor in numerator and denominator, so it cancels out and it leads to a simplified form which could be written as 1 over 2 minus x. Or let me take minus also common, and I write here 1 over minus 1 over x minus 2. Now, when we cancel this out, at this time we write our restrictions as x is not equal to 0 and is not equal to 2. What are our restrictions here? Since we have vertical asymptotes at minus 1 and plus 3, our restrictions here are that x is not equal to minus 1 and x is not equal to 3, okay, which you can see from here, right? At both these points we have vertical asymptotes, right? We call this kind of an discontinuity as an infinite discontinuity because our function moves to infinity at this point. Do you see that? Now here what happens really that we have a common factor. Because of that they cancel out, but still the discontinuity remains, correct? So this kind of a function can be drawn here like this. I'll squeeze it in between. So we have a discontinuity at x equals to 2. Let's say this is my x equals to 2, and that is a vertical asymptote. Plus we also saw that x is discontinuous at x equals to 0, right? When we cancel out the factors, we have a different kind of discontinuity. We call this to be a hole. See, there is no vertical asymptote at x equals to 0, correct? Because it cancelled out. So whenever we have a common factor in numerator as well as in denominator and they cancel out, then we do have a restriction, and the restriction is x cannot be that value, which makes it 0. But at that point we have a hole and not a vertical asymptote, correct? So x equals to 0 will lead us to a hole at x equals to 0. Now if you plug in the value here, you get 1 over 2. So at x equals to 0 the value should be half, and that value is a hole, not a filled in, a hole where the domain is not even. When we make a hole, then from the domain we exclude x equals to 0. As you can see, this function is like a reciprocal function shifted 2 units to the right, and what does this minus reflect? Reflected on the y-axis. So if you draw this function, it will kind of look like this. Correct? So here you notice two different types of discontinuities. One is because of vertical asymptote, which is at x equals to 2, and the other one is a hole, and this is a hole at x equals to 0. Do you see that? So whenever you have a common factor which cancels out, it leads to a discontinuity like this, like a hole. Okay? It is not necessary that every rational function will have a discontinuity. Let me give you one example. Let us say we have r of x equals to 1 over x squared plus 1. Now, discontinuity could be if the denominator is 0. If I equate x squared plus 1 equals to 0, do I get a solution? Let's say x squared plus 1 equals to 0 will lead to x squared equals to minus 1. But x squared is always positive, is never equal to minus 1. Therefore, denominator is never 0. Can you sketch a graph of this function? That is an exercise. And I have sketched this graph in the other videos. You can look into that. Correct? So, you can try some examples and then figure out what kind of discontinuities we have. It is not necessary always to see a rational function as 1 over x transformed, kind of. I'll give you an example here. Let us say, let me give you some more examples and check if you can draw those graphs. Let us say we have g of x equals to 2 x minus 1 over x minus 1. Let me make it x minus 1 times x plus 1. Right? X minus 1 times x plus 1 is x square minus 1. I could have written that also. Now, I am writing in factored form to make things very simple for you. Will this graph have a vertical asymptote or a hole, or what kind of discontinuity will it have? Well, as you can see from here, we have a common factor which will cancel out. So once we do that, then we are left with a line. Do you see that line? It says 2x plus 1. So the question here is, are these two functions g of x 2 times x minus 1 times x plus 1 divided by x minus 1 exactly same as 2 times x plus 1? They look like, because we cancelled out. But there is a huge difference, and the difference is of restriction. Whenever we cancel this out, we should always write x is not equal to 1. Now they are exactly same. Do you realize that? Earlier they were not. Without restriction, this function is not same as that. Without restriction, this is simply a straight line. Do you see that? So now, when we have put the restriction in place, we can draw this function. And this function will look something like this. I'll just draw a light line and then put that hole at x equals to 1, okay? Because it is not permitted, right? So x plus 1 is kind of from 1 a line, straight line like this, correct? Now, as you know, we have a restriction. At 1, we cannot have any value, right? Because it is not in our domain. So we should have a hole in 1. So at 1, this value should be 2. So at 1, let's say this is our 2, we put a hole here. And our graph is now this line. Do you see that? With a hole here, right? This value is 2 and this is 1. So that represents the rational function. And do you notice the shape? It's like a line, right? The shapes could be different, okay? Now, as an exercise, you can try figure out discontinuities in the following functions. Okay, and see if you understand. If there is a difficulty, you can place your comments and I'll happy to answer your questions. Thank you.